So on to chapter 5, which is correlation, and we're starting off with the PMCC, Pearson's product moment correlation coefficient. Usually we just say PMCC or R. When we first started with scatter diagrams, we would say something had, say, a weak positive correlation or a strong negative correlation, and then we started using values for R. So we said R equals 1 is a perfect positive, R equals -1 perfect negative, R equals 0 is no correlation. You will still be asked to possibly plot a scatter diagram, infer some things from the diagram, such as any obvious outliers, and you'll also get a rough idea of the value of R. So if you've got a scatter diagram and everything, all the points are reasonably close to a straight line, and they're going in the positive direction, you would expect your value of R to be somewhere near 1. Now we need to calculate R, and the formula is in the formula book, but it isn't the most appealing formula. So I call this sexy maths because we have SXX, SYY, and SXY. Sexy always goes on top, so you can have something to look at. So R equals SXY over the square root of SXX, SYY. Okay, that looks a bit of a mouthful. It looks like a lot of work, but it's actually reasonably straightforward. Most of the time, we're going to use the second versions of these equations. So this part, and this part. These are just summary stats. You may be given the summary stats, or you may have to work them out from your calculator. And we're going to do some quick calculations now. So we're going to start with just some straightforward examples. So the first one, we're given the summary stats, which is quite common because that means you can't directly get R from your calculator. So we just need to work out each section of the formula. So SXY is sum of XY minus sum of X, sum of Y over N. SXX is sum of X squared minus the sum of X squared over N. And SYY is the sum of Y squared minus the sum of Y squared over N. So if we just put those values into our calculator, so sum of XY is 5611 minus 147 times 252 over 7. This value here is 3307 minus 147 squared over 7, because n equals 7 because we've got 7 pairs of values, and 10028 minus 252 squared over 7. So what these values equal? So these values equals, this one's 319, this one is 220, this one 956. So now we've got those values, we just stick it into the formula. So R is SXY over SXX SYY. So that gives me 319 over the square root of 220 times by 956. Put that into a calculator and we should get about 0.696 to 3SF. Okay, reasonably straightforward. For the second one, the marks of a random group of 10 8-year-old pupils in their latest reading and spelling test are given below. So here we're given the raw data. So the first part says draw a scatter diagram. I'm not going to draw the scatter diagram. You can draw the scatter diagram yourselves. But when you do draw the scatter diagram, it appears that there is a weak positive correlation. Okay. Now we need to do the PMCC. So we go to menu and then we go to 6 and we are going to go to 2. Okay. So this gives us an X and Y and possibly a frequency. We don't need the frequency in this case. So we just fill in the values. So I've got 4, 10, 9, 7, 6, 5, 7, 9, 8, 6 for my X values, and then for my Y values I've
got 8, 6, 10, 5, 8, 4, 8, 9, 7, 4. Then option, and if we go to 3, that will give us our summary stats. So we get our summary stats from there. So I've got sum of x equals 71, sum of y, sum of x squared equals 537. I've got sum of y equals 69, sum of y squared equals 515, and I need sum of xy as well. Sum of xy is 502. Okay, if you go back and we go to option 4 instead, it does give you what R is. Okay, it also gives you A and B for the regression. So I'm just going to make a note of that. So you shouldn't just say what R is straight from there, but it can be a useful thing to check. So R equals 0.338. Okay, that's what I'm aiming for. So now I'm just going to put these into these formulas. So I need to find SXY, SXX, and SYY. So SXY is going to be sum of XY, so that's 502, minus the sum of X, 71, times by the sum of Y, 69, divided by 8, because N is equal to 8. SXX is going to be 537 minus 71 squared over 8, and SYY is going to be 515 minus 69 squared over 8. Okay, we put these into our calculator, we get SXY is 12.1, we get SXX equals 32.9, and then SYY is 38.9. Then we need to work out what R is. So R is SXY, so 12.1 divided by the square root of 32.9 times by 38.9. If I do that in my calculator, so 12.1 with the square root of 32.9 times by 38.9, and we get 0.338. So we get the same answer as what we got from the calculator. Okay, never just go straight to R equals this, always show some intermediary steps. These are all the intermediary steps you need to show. Okay, this could be like a 4-mark question, so this isn't that much to write for such a question. Okay, on to hypothesis testing.
So just some quick points before we go into hypothesis testing. Any linear coding of either variable does not affect the correlation coefficient. So if I multiply the value of x and add a value, that will not affect my value of R. This works for PMCC and Spearman's rank, and we'll show that towards the end of this chapter. To be safe, you should write down at least SXX, SYY, SXY, and R in your questions. So you can find R straight from your calculator if you've got the raw data, but to be sure, make sure you're getting all the marks, write down at least SXX, SYY, and SXY, as well as R. So that means you can pick up your method marks if you do any of the calculations wrong. Now, hypothesis testing. So you'll be determining whether there is evidence for correlation in the population from which your sample is taking. What we do is we compare the PMCC to a sample of data with a critical value which varies according to the size of the data set from your formula book. So here we are comparing to a critical value in your formula book. Now this is different from comparing a probability value, okay? Because what you actually do is do the opposite. So if I'm got a probability and I'm comparing it at, say, the 5% level, if my probability is less than my significance level, then I will reject H0. Here, if my value is bigger than my critical value, then I reject H0. So it's the opposite way around. a quick point is that the test is only valid if the data is drawn from a normal bivariate distribution. Now, you don't know what a normal distribution is yet, but you should have some idea. It's one which looks like a bell curve. It's how like grades are sorted out, and how height is distributed, how weight is distributed. Bivariate just means two variables. And the calculation of the PMC gives R, which is the sample PMCC. Rho, this symbol here, which is used for density, is also used for the correlation coefficient of the population, or the parent distribution. So your hypotheses will only involve rho. Now, what are the steps? So first thing, as always, write down the null and alternative hypotheses. This is in terms of rho. Then we need to write down the significance level, calculate the product moment correlation coefficient, unless it's already given to us, look up the critical value from the table, then compare the value of R to the critical value. Okay, we're just comparing the magnitude, so the modulus of R. So if we get a negative value of R, we're still comparing the positive version of it to the critical value. So if it's greater than the critical value, then reject H0, then we need some summative statements. So there is sufficient evidence to suggest blah, 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 blah. Okay, and always make sure it is in context. So I'm going to do a quick example now.
So walking through a hypothesis test question. So a researcher wishes to find out if there is any connection between the length of time young children spend on screen and their reading ability. So this is a two-tailed test. We're not looking for a positive or negative, we're just looking for any connection. She collects data on 57-year-olds, summarised below. So we've got the summary stats. Carry out a hypothesis test at a 5% level to determine whether there is any connection between screen time and reading ability. So the first thing we need to write is our hypotheses. But before we do that, we need to state what rho is. So rho is the population correlation coefficient. Okay, so rho is the population coefficient. Then our H0 is always rho equals 0. So there is no correlation. And H1 would be rho is bigger than 0, less than 0 if it's a positive or a negative. But this is two-tailed, so we're just doing rho is not equal to 0 because it's two-tailed. And it's at the 5% level. So now we need to work out what R is. So we need to work out what our values are. So we've got SXY, so that's sum of XY. So XY minus sum of X, sum of Y over N, SXX, sum of X squared minus sum of X squared over N, and we've got SYY, sum of Y squared minus sum of Y squared over N. So SXY is 11846 minus 222 times 2892 over 50, because N is 50, because I've got 57-year-olds. Stick that into our calculator and we get minus 994.48. We can get negatives, it's fine, because we can have negative correlations. SXX, so that is 1604 minus 222 squared over 50 gives me 618.32, and SYY is 179,558 minus 2892 squared over 50 gives me 1284.72. So now we can work out R. So R is SXY, SXX, SYY. So that's the same as minus 994.48 over the square root of 618.32 times 1224.72 Put that into a calculator and we get minus 0.3068. So that is our value for R. Now we need to compare this value of R to something, so we need to use our critical value table. So this is the critical value table. Okay, it's split into R and RS. We're just looking at R for now. Okay, this is a two-tailed test at 5%. So here we've got one tailed and two tailed. So two-tailed at 5%. Our n is equal to 50. So we need to go down to n equals 50 here. So we've got n equals 50. So two-tailed test at 5%. Our critical value is 0.2787. This value here. So critical value equals 0.2787. A reminder that we compare our magnitude of our R, so our modulus of R, to our critical value. So we'll keep doing it in red. So because my modulus value of R is bigger than my critical value, that means I'm rejecting H0. Okay. Then I need my summative statement at the end. So my summative statement will be: there is sufficient evidence to suggest a correlation between screen time and reading ability. Okay, that is a perfect answer for 4 marks. I'm going to do one more example and then we'll move on to Spearman's rank. So here's an example with some raw data. So it's generally thought that the taller a person is, the heavier they are. As a short lad, I'm obviously the exception to the rule. A random selection of 11 students is measured. The following are the results. First part, calculate the product moment correlation coefficient. So because we've got some raw data, we need to get some summary stats. So to save time, I've already typed these in. So menu 6, 2, type the data in, and then once we've got the data, option and 3. So I've got sum of x equals 724, sum of x squared equals 47774. Then I've got sum of y equals 1406, sum of y squared equals 181040, and sum of xy equals 92819, and n equals 11. So we need to find our values. So sxy, sum of xy, sum of x, sum of y over n, sxx, sum of x squared minus sum of x squared over n, and syy, sum of y squared minus sum of y squared over n. If I put these values into my calculator, so for sxy I get 278.636. For sxx I get 121.636, and for syy I get 1327.636. So r is sxy over square root of sxx, syy. So I've got 278.636 over the square root of 121.636 times by 1327.636. Put that into my calculator and I get 0.693 to 3SF. Okay, moving on to question 2. State the null and alternative hypothesis. So first we need to say what rho is. So rho is the population coefficient. Correlation coefficient. Then my H0 is always rho equals 0. Whoop. And my H1, because it's generally thought that the taller person is the heavier they are, that's assuming there's a positive correlation. So rho is bigger than 0. So that means this is a one-tailed test. Then part 3. Carry out the hypothesis test. So I've got my value of R, I've got my H0, H1. Now I just need to find my critical value. So for my critical value, again looking at the left hand side, so it's a one-tail test at the 5% level where n equals 11. So n equals 11, one-tail test at 5%, and I get the value of 0.5214. Okay, so my critical value is 0.5214. And my value of R is 0.693. So because R is bigger than my critical value, this means I am rejecting H0. Then a nice summative statement. There is sufficient evidence to suggest a positive correlation between height and weight. And finally, a student suggests that a positive correlation between height and weight implies that the taller the person is, the heavier he or she will be. Comment on this statement. Here's your famous correlation question. So correlation does not imply causation. Okay, that's good enough for just a mark, but just to elaborate a bit more, just because something is correlated doesn't mean one causes the other. Yeah, there's the famous example of on the X value, it's the amount of ice cream sold. On the Y value, it's the amount of people being killed by sharks. And there's almost a perfect positive correlation between them. But that doesn't mean that more people buying ice creams causes more people to be eaten by sharks. There's a confounding variable, which is temperature. Okay, so there may be a confounding variable. Okay, on to Spearman's rank.
Now on to Spearman's rank correlation coefficient, which we label with R with a subscript of S. So when we have data which is not from a normally distributed population, we rank the data and then perform a correlation test on the ranks. So it does not matter whether we rank ascending or descending as long as it's consistent. And Spearman's rank differs from PMCC because the PMCC, or just normal R, is a measure of how linear the data is, whereas RS is a measure of how much one variable increases or decreases with the other. So although we're not using the raw data in a Spearman's rank because we're just ranking the data, it can be a stronger test because we can look at non-linear associations. So we can look at, say, exponential examples or reciprocal examples. Whereas the PMCC is literally testing, do the values go in a straight line? The formula is quite straightforward, and we're going to do some examples and again some hypothesis testing with it.
The formula for RS is 1 minus 6 sum of d squared over n squared minus 1, where d is the difference between the ranks of each item in the paired data. Before I go on to an example, just a quick point about R and RS. So R is linear, whereas RS is non-linear. So if I have R equals 1, that means that RS is also equal to 1. Yeah, if I've got values which are going in a perfect straight line, RS is just a way of saying if x increases, y also increases. So that means that's going to be a straight line for both. But if I have rs equals 1, that does not mean that r equals 1. So if I have, say, values going up like so going up in a exponential way like that, that will have rs equal to 1. Okay, but that will have r close to 0 because I can't draw a straight line between all the points. But as one increases, the other increases, so rs is equal to 1. Okay, so that's just as a quick aside about the difference between r and rs. So in a competition, 8 students were ranked as follows by the judges. So we've got entrance A to H, first judge and second judge. What is Spearman's rank correlation coefficient? So if rs equals 1, it means that the two judges are in perfect agreement. Rs equals -1, perfect disagreement. R equals 0, they're just randomly choosing. So I need to work out what D is. Okay, I can do the first take away the second, or the second take away the first, it does not matter. So I'm going to do D is the first take away the second. Okay, and I know that N equals to 8, because I'll probably use that in a bit. So for D, so 2 take away 5, minus 3, 4 take away 2, 2, 1 take away 3, minus 2, then I've got 1, and I've got 2, 1, I've got 1, and I've got minus 2. Then I need to square these values to get rid of the negatives. So 9, 4, 4, 1, 4, 1, 1, and 4. Add them up. So that gives me sum of d squared equals 28. Now I just put it into the formula. So rs is 1 minus 6 times the sum of d squared, 28, over n, which is 8, times by 8 squared minus 1. Put that into our calculator, we get 0.667 to free SF. And that's it. That's how easy it is. So finding RS, really straightforward, and the hypothesis testing is pretty much the same as with the PMCC as well. Now there are two big differences between Spearman's rank and PMCC for hypothesis testing. The first is we don't use rho for our H0, H1. We say there is no association, there is an association, there's a positive or negative association. Okay, the reason being is we don't know what the association is. It could be non-linear, it could be quadratic, it could be exponential, it could be whatever, so we just say association instead. So we don't use rho. And the other thing is we use the right hand side of the critical values table because this is RS rather than R, but we'll get back to that. So standard question, 2 wine experts, wine a favourite of my wife's, ranked 8 wines, chosen at random from 1 to 8, best to worst. First, calculate Spearman's rank correlation coefficient. So the first thing I'm going to do is work out what D is. So D, so I've got minus 2. Again, I'm doing 1 take away 2. 2 minus 2, 4 minus 3, 1 and minus 1. So D squared 4, 1, 4, 4, 16, 9, 1, 1. Add them together and I get 40. So RS is 1 minus 6, sum of d squared over n squared minus 1. So that means in this case it is equal to 1 minus 6 times 40 over 8 experts, so 8 wines, 8 squared minus 1. Do that and I get 0.524 to free SF. Okay, part 2, state suitable, null and alternative hypotheses. So H0 would be there is no association. Between the scores given. By the 2 experts. Whereas H1 will be there is we're seeing whether experts are basically in agreement. So that's a positive association. So there is a positive association. Between the scores given by the two experts. I know it's annoying to write it out and we can't just use row, but it's worth at least a mark. On to part 3. So carry out the hypothesis test at a 2.5% significance level. What is the conclusion? So we need to work out our critical value. So critical value. So we've got RS over here. We've got n equal to 8. And we want to do a one-tailed test at 2.5%. So 2.5% one-tailed, n equals to 8. I've got my critical value being 0.7381. Yeah, so critical value 0.7381. Now my value of R is 0.524, so that's not big enough. So my value of R is less than my critical value, so that means I am accepting H0. Then we have our summative statement. So there is insufficient evidence to suggest a positive association between the scores given by the two experts. Okay, I'm going to do one more example and then it's onto coding. So the infamous question in my classroom, because more than half my students get it wrong. That may be a reflection on their teacher, but I think I've just picked a particularly tricky question. So in a geography project, a student wished to investigate whether there is a relationship between rainfall and peak stream discharge. He does not expect the data to be bivariate normal, so decides to test for rank correlation. The following data were gathered. Calculate Spearman's rank correlation coefficient. Now, this data is not ranked, so we need to rank them. Okay, I'm gonna rank them from smallest to biggest because that makes sense to me. So ranking from smallest to biggest. So that means my rainfall rank and my discharge rank. So if I'm ranking smallest to biggest, I have 2, 4, 8, 7, 3, 5, 6, 1, because my smallest is 0.5, then my next one is 1.3, then my next one is 1.8, and for my discharge rank I've got 4, 2, 8, 7, 3, 5, 6, 1, because again my smallest is 1.9 and my biggest is 7.9. So now I can work out my difference, so my difference, so minus 2, 2, and then those are all the same. So d squared is just 4 and 4. So sum of d squared equals 8. So for RS, I know n equals 8 as well, because I've got 8 data points. So RS is equal to 1 minus 6, sum of d squared over n squared minus 1. So that means I've got 1 minus 6 times by 8 over 8 times by 8 squared minus 1. Put that into my calculator and I get 0.905. Okay. Now for part 2 and 3 I'm going to go up here. So part 2, state suitable, null and alternative. So H0, there is no association. between rainfall and stream discharge. H1, I'm just investigation whether there is a relationship, not if it's positive or negative. So this is two-tailed. So there is an association. Between rainfall and stream discharge. Okay, part 3, carry out the hypothesis test. So we need to work out our critical value. So critical value, this is a two-tailed test at 5%. So two-tailed 5% when n equals to 8. So my critical value is 0.7067. So critical value, two-tailed test, 5%, n equals 8, 0.7067. Okay, my value of R is bigger than my critical value. That means I am rejecting H0. And nice summative statement. There is sufficient evidence to suggest an association between rainfall and peak stream discharge. That's it. On to coding.
On to the last part, which is regression line. So a regression line is the most accurate line of best fit, which minimizes the square of the distance between the line and the point, assuming that the x values are accurate. Now, this sentence may look like absolute rubbish. So let's have a little visual example. So here I've got some points, and I'm trying to fit a line between them. Okay. What my regression line does is if I take the squares from each point, I'm trying to minimize the total area of those squares. So this is why this is usually called the method of least squares, or least squares regression line. And all we do is we just use a formula to do this. Our calculators can find the line quite straightforward, but again, you'll have to show some detailed reasoning in most of these questions. And just some quick recaps. So an independent or exploratory variable is on the x-axis, whereas the dependent or response variable is on the y-axis. So the independent variable is one which just goes up in increments, so it's usually time, and y is due to the value of x you've chosen. And interpolation, which is good, is when you estimate the value of a dependent variable within the range of the data, and the opposite is extrapolation, which is bad, because that's when we use our line of best fit to predict outside our data range, so either really small values or really big values. We shouldn't do that because we don't know what the values look like outside of our data range. Yeah, it could look completely different, it could spiral out randomly, so we don't know what it looks like. The formula, straight from the formula book, so we're using SXY and SXX again. So the regression coefficient of y on x is b is sexy over SXX, and the least squares regression line of y on x is y equals a plus bx, where a equals the mean of y minus b times the mean of x. Again, a reminder, because this is so important, your calculator can do it straight away, but these are usually detailed reasoning questions, so you will have to write some intermediary points in. Okay, on to examples.
So starting really slowly, so for the following bivariate data, obtain the equation of the least squares regression line of y on x, and then estimate the value of y when x equals 21. So I've got the raw data, so I just need to put it into my calculator. So again, menu 6 and 2, my x, so 10, 11, 15, 17, and 22. And my y values, 25, 23, 17, 14, and 11. Option, and again, if we press 4, it does give us the correct values, so we're just going to make a note of those. So A equals 35.87, B equals 1.19. That's what we're aiming for. But this will be a detailed reasoning question, so we need to use part 3 there. So what do we need to write down? So we need to write down sum of x. So sum of x equals 75. We need to write down sum of x squared. So sum of x squared is 1219. I need to write down x bar as well. Also, x bar equals 15. Then I've got y bar as well. So y bar is equal to 18. Sum of y. Do I need sum of y? I don't need sum of y because I've got nothing to do with SYY, but I do need sum of XY. Oh, so I do need sum of y. Whoop. So sum of y equals 90. And sum of XY equals 1238, and we know n is equal to 5. So now we can put everything into our calculator. So SXY is sum of XY minus sum of X, sum of Y over n. So that means I've got 1238 minus 75 times by 90 over 5, and I've got SXX, sum of x squared minus sum of x squared over n. So I've got 1219 minus 75 squared over 5. Okay, this gives me SXY is minus 112, SXX was 94. So now I need to work out what A and B are. So B is SXY of SXX, so minus 112 over 94. Minus 112 over 94. Hopefully that's 1.19. Yeah, minus 1.19. That must have been minus 1.19 when I did it on my calculator. So equals minus 1.19 to 3SF. And A is y bar minus B x bar. So y bar is 18 minus 1.19. That's by x bar is 15. So A is 18 plus 1.19 times 15. 35.8, yeah? 35.9 to 3SF. So I've got the values I expected. So then I need to put that into a form, in the form y equals mx plus c. So I've got y equals 35.9 minus 1.19 x. Okay, this is just y equals mx plus c, just written in this way because of economics. Ugh. The last part of the question, estimate the value of y when x equals 21. So at x equals 21, means I've got y equals 35.9 minus 1.19 times by 21. This is fine to do because this is interpolation. 21 is in my data set. Yeah, this goes up to 22. So 35.9 minus 1.19 times 21. And I get 10.91. So 10.9 to 3SF. Yeah, that's not too tricky. I'm going to do 2 more examples. So the following table gives the ages and blood pressure of a random sample of 10 men. First, I need to find the PMCC. So I need all of SXY, SXX, and SYY. So to save some time, I've already typed the values in. So menu 6.2. and I'm going to make just a quick note of what R is. So I've got what I'm aiming for is A equals 92.8, B equals 0.84, and R is equal to 0.84855. Okay, that's what I'm aiming for. Right, option and 3. Let's write down some values. So x bar is 50, sum of x is 500, sum of x squared 26888. Next I go to y bar, so y bar is 135, sum of y equals 1350, and sum of y squared equals 184088. Sum of xy equals 69092, and I know n is equal to 10. Right, let's work out some values. So sxy, sum of xy minus sum of x, sum of y over n, sxx, sum of x squared minus sum of x squared over n, syy, sum of y squared minus the sum of y squared over n. Okay, putting these values in, I get sxy equals 1592, sxx equals 1888, and syy equals 1838. So R is sxy, sxx, syy. Put that into my calculator, I get 0.855 as expected. All good. Now I need to do part 2. So for part 2, I'm doing A and B. So B is sxy over sxx. So 1592 over 1888, which gives me 0.843 as expected, and A is equal to y bar minus bx bar. So that's 135, take away 0.843 times by 50. Put that into our calculator and we get 92.8 as expected. So that means my formula is in the form y equals a plus bx. So that means y is equal to 92.8 plus 0.843 x. And then part 3, estimate the blood pressure of a man aged 43. This is fine because it's interpolation, not extrapolation. So at x equals 43, I've got 92 at y equals 92.8 plus 0.843 times by 43, and that gives me 129 to 3SF. Okay, now we just need to finally go into coding. So what do I mean by coding? So coding is when I do a change to the values of x and y so that I get them in an easier form. So for example, if I've got lots of values which I like so I've got like 1,000,003, and I've got say 1,000,007 and like 1,000,009 and like 1,000,004. If I just take away the million from each of them and make these values 3, 7, 9 and 4, okay, I can find the line for these values and then code them back into the previous values. So doing the calculations with these values is obviously going to be easier than the values with these ones because they're smaller numbers. So as an example, so 8 samples of carbon steel were produced with different percentages C of carbon in them. Each sample was heated in a furnace until it melted, and the temperature M in degrees Celsius at which it melted was recorded. The results were coded such that X equals 10C and Y equals M minus 700 over 5. Coded results are shown in the table. Calculate SXY and SXX. Find the regression line of Y on X, and then find the equation of the regression line of M on C. So we need some summary stats again. So menu 6, 2, X values 1, 2, 3, 4, 5, 6, 7, and 8. And our Y values are 35, 28, 24, 16, 15, 12, 8, and 6. Option and 2. So I've got X bar equals 4.5, sum of X equals 36, sum of X squared equals 204, Y bar equals 18, sum of Y equals 144, sum of Y squared equals 3310. So SXY, sum of XY minus sum of X, sum of Y, and SXX, sum of X squared minus sum of X squared, N. I didn't write sum of XY. Sum of XY is 478. It's given to you in the question as well. So I've got 478 minus 36 times 144 over 8, giving me a value of SXY of minus 170, and SXX equals to 204 minus 36 squared over 8, giving me a value of 42. So this is part A. On to part B, so find the regression line of Y on X. So for B, so I've got Y equals A plus BX, where B equals SXY of SXX, and A is Y bar minus BX bar. So B is minus 170 over 42, which is minus 4.048. And A is 18 minus 4.048 times by X bar, which is 4.5. That gives me a value of 36.216. Meaning my Y is equal to 36.216 minus 4.048 X, but this is not in, so. And then part C is the coding part. So find the equation of the regression line of M on C. So here I'm just replacing the values of X with 10C, replacing the value of Y with M minus 700 over 5. So Y is equal to M minus 700 over 5 equals 36.216 minus 4.048 times by 10C. Okay, so I just need to rearrange this. That gives me M minus 700 is equal to 181.08 minus 202.4 C. Then I add that 700, so M equals 881.08 minus 202.4 C. So from my Y and X, I can then change it into M and C. And that's it. That is chapter 5 done.